Hello and welcome to Calculus Chat, a weekly discussion with your lecturers for 114. I'm Dr. Biggs, and here with me as usual is Dr. Kellerman.
Hello.
And Professor van der Walt.
Hi.
Wow, can you believe that we're already 3 weeks in?
Yeah, I'm exhausted.
Yeah, it's about 20% done.
So I think our students are exhausted as well.
Yeah, it looks like it. So well, what have we been up to that we are so exhausted? Well, we've done the worksheet 3, which was on the second week of lectures, right? And we had lots of good questions there. I think particularly what I've seen a lot of students engaging in is questions about proving that something is true, or rather, looking at a statement and deciding whether it's true or false. That in itself is difficult. Then if we think it's true, to try and prove it, and if we think it's false, to try and give a counterexample.
Yes, you can't prove a universal statement true with a single example. So if you have a statement, every sheep is black, you can't prove it by showing an example of a black sheep and saying, well, here's a sheep and it's black, so this shows that every sheep is black.
Yes, so that is definitely one of the hurdles our students encounter.
Although you can, of course, if it's an existential statement, like there exists a black sheep, that you could prove with an example. In fact, the obvious way to prove something like that would be with an example.
Look, there it is. It exists.
Should we tell the joke about the economist, the physicist, and the mathematician flying over the Karoo?
Go ahead.
Well, so they're flying over the Karoo. Well, I guess they were driving through the Karoo. They pass a hilltop and there's a black sheep on the hilltop. And the economists say, I didn't realize that the sheep here in the Karoo were black. And the physicist says, well, no, you can't say that. All you can say is that there is a black sheep here in the Karoo. And the mathematician says, well, no. Actually, all you can say is there exists a hilltop in the Karoo on which there is a sheep, at least one half of which is black.
Beautiful. Oh, no. And of course, the other problem is you can't prove something true, which is actually false.
Yes, well, you can try.
And try you can. And I mean, I think that is often the difficulty is there's this tension between whether you try and prove that it's true or whether you try and prove that it's false. And I think even as accomplished mathematicians, we will often dance this dance between true and false. We'll see a statement, you think, maybe I think it's true, and you spend some time, maybe a few days, trying to prove it true, and you just can't get it true. So then you spend the next few days trying to prove it false. And jeepers, you just can't get it false. And through that process, you start learning something, right? And finally, you get one of them.
Yes, I mean, if I think of the theorems I've proven in my life so far, very few of them turned out the way I thought they would when I started.
Aha.
Usually it turns out that, but you need some extra condition, or, oh, no, wait, it actually works more generally. And sometimes it turns out that, it never works at all.
Indeed.
But I've always learned something from it.
A spare thought for the mathematicians who spent hundreds of years trying to prove the parallel postulate from the other axioms of Euclidean geometry, and only to eventually discover that it can neither be proved nor disproved from the other axioms. So that's the third possibility is the thing you're trying to prove may happen that it cannot be proved nor can it be disproved.
Hopefully, we will not ask our students to prove or disprove something that cannot be proved.
Well, there are some of those statements which turn out to be independent of, which turn out not to be, which you cannot prove or disprove, are actually quite simple.
Yeah.
I think it was Julia Robinson who in the 60s exhibited a class of Diaphantine equations for which the existence of integer solutions is independent of the axioms of mathematics.
The beauty.
I mean, one of these, an example of a Diaphantine equation is this famous Fermat theorem, x to the n plus y to the n equals z to the n.
Mm-hmm.
And here Andrew Wiles locked himself up for how many years trying to prove this. And I mean, just think about it. If it turned out that this thing was unprovable. Now, it turned out it's provable, the conjecture is true, but it could very easily have turned out not to be provable.
Indeed. Well, I think at least he will have learned something on the journey of decades in his attic.
Yes, shame.
No, I mean, so this is. I mean, even some of these simple examples. If I go and have a
Yeah.
look at those tutorials, it's not immediately obvious to me, and sometimes I will start down the wrong road. I think it's true, and then I
Mhm.
start and try and prove it, and it's only by engaging with the question and trying
Yeah.
one of the roads that you actually learn enough to see what is the right way.
Yeah, yeah, because you think, okay, this is going to work. Let me try it, and then you start doing what you think is going to work, and then you realize, oh, but it doesn't work. Oh, okay, it's not true.
And often, I mean, that path you go down helps you see why it isn't working. In your proof, you see, oh, I can't make this step. Ah,
Mm,
so a counterexample might be something that's going to happen exactly here where my proof is failing. It must have that property that will contradict the property I need in order to make that step. And then that's often how you find a counterexample. And often that's also the way that you end up starting to modify your statement. You say,
mm.
okay, well, my statement isn't going to work in full generality, but maybe if I specialize it, if I only take functions of a certain type or a special kind, then it might work.
Yeah.
Yeah, there's a question in worksheet 3, prove that every injective function is either increasing or decreasing. And that one is really giving even the top students a run for their money.
Mm,
Because if you try and prove it, then you run into difficulties, and finding a counterexample is not entirely obvious if you're not in the mindset of thinking about discontinuous functions.
mm,
Exactly. And I mean, that's, I think, part of the point of some of these questions is to broaden the mind. Is often so when we're doing problems, we only have a certain kind of function in our mind when we're thinking about functions. And we need to be careful because, well, that's not all functions. And if you want to make statements about all functions, you have to talk about all functions. So, anything else crop up on the Discord or on the in tutorials?
I don't know if this is the right place to discuss it, but there was an interesting question. How do you explain to somebody who's never heard of a mathematician what a mathematician is?
Oh, I saw that was
Yeah.
beautiful.
It really got me thinking. I mean, I should have been making video lectures, and I was thinking about this question.
It's a tricky question. I mean, and I think it's a question we've all faced as
Yeah.
mathematicians. Somebody asks you, "What do?" You say you're a mathematician. You can just see them shut down.
Or you mean like an actuary?
That's the other thing that happens. Yeah.
No, it's not the same.
Yes, I've found many people think that mathematics is basically complete, that it's about solving equations, and mathematicians know how to solve the various types of equations. And if you tell them that you do research in mathematics, they seem to be quite surprised.
So, Jan, Adam, do you want to share a little bit what your response was?
Well, I think the correct answer, which sounds a bit flippant, is that a mathematician is somebody who does mathematics. And the reason why people are unsatisfied with this question is because they don't understand what mathematics is. And I mean, if you think about your typical, say, school mathematics education, then that is not surprising that you would have the kind of idea that everyone mentioned, that mathematics is this a complete set of body of knowledge, and all we do as mathematicians, crank the handle, solve the equation. But to be honest, I can't imagine anything more boring than doing that all day.
Yeah, we're not computers, we're mathematicians.
No, and I mean, I love mathematics. I love doing mathematics, and I don't want to do something that boring.
Absolutely.
Yeah. So then the question really that should be answered is, what is mathematics? And that's
Yeah, no, I mean that's a tricky question and one that me and Ida tried to answer a little bit in our introductory video, and our view or our attempt at answering that was to say that, well, it's all about finding patterns and abstractions of those patterns,
yeah.
and we did a nice example of where you can play two games, tic tac toe and a little word game, and showing that, well, actually the abstract structure behind those two games are
Mm.
exactly the same.
Yeah, I think that's an excellent description of what mathematics is. It's about recognizing patterns and then kind of crystallizing these patterns in an abstract language.
It's contrary to popular impression, I would say numbers are a part of mathematics, but mathematics is not numbers. It's so much more than just numbers. So
Oh
it's
yes.
not the study of numbers as such. It's more the study of ideas, rigorous study of ideas.
Yeah.
Yeah, no, I think if you our students might be shocked to see some dissertation theses that have very few, if any, numbers in them.
Yes.
Yes.
Well, at least there are at least as many numbers as there are pages. So you have a lower bound.
Only if the pages are numbered.
Yes. Let's assume they're numbered.
Okay. So, what did we do in lectures? Well, Professor van der Walt started us off on the big conceptual tool that we'll be using, which is the limit, right? And we looked at the definition and maybe a little bit at where did it come from? What was its inspiration? We need to build some intuition about what does this limit mean, and then also look at the more formal way of capturing this idea.
In my own experience, I think the epsilon delta definition of a limit when I was an undergraduate, it was one of the highlights of my mathematics education. I found it such a beautiful idea and yet so simple.
Yes, absolutely. If you capture that idea in such a concrete and synthesized way, and it really is powerful because it really crystallizes beautifully exactly what you are talking about. But it is a tricky idea, maybe the first time to get your head around. This is very often, if you just look at it seems very weird. And
Yeah.
for me, you mustn't get stuck on the symbolism, right? The way we express it. You have to start from, what is the idea? What is it that we're trying to express? And then
Mm.
how is it that the statement is capturing that idea, the essence of it?
Yeah, I tried to bring something of that across in the lectures, particularly in the first lecture,
Mhm.
because it is. I mean, to come up with the right concept of limit, because you start off saying things that seem okay, but then if you work out, then you can come up with an example which tells you no, but my original idea for how to define limit is wrong, because here this completely absurd thing happens.
Mhm.
You have to go back and say, okay, well, no, let's be more precise. And then eventually, by sort of this process of refining your definition until you get something which captures exactly what you want, then you arrive at this definition. And it is a great definition. And it is a tough definition. It's
Mhm.
beautiful, but it's tough. And I don't want the students to get stuck on that definition. It's important, and you will spend a lot of time with this definition next semester and in your second year and in your third year. But so you should spend some time trying to understand it, but you should also spend a lot of time trying to develop your intuition, see what's going on,
Yeah.
try to understand the thing as opposed to getting stuck on the formalism.
Yes, I mean we are introducing the formalism now so that you can start getting used to that language. But at this stage, we also are focusing very much on what is the idea behind the limit and
Yeah.
developing our intuition. The formalism we will be returning to over and over again as you develop mathematically. And I think there is, and I've already seen in one of the Q&A sessions, I think a bit of tension here between the intuition, right? Developing the idea of what's
Mm.
going on and sort of having a hand waving argument for why the limit goes off to infinity, and having
Mm.
the formal proof and the formal manipulation to actually prove that indeed that is the case.
Yeah. Yeah, that is true. Look, and the other thing is there are so many different situations that can come up that it becomes counterproductive to try and write down theorems that deal with all of them.
Exactly.
Right. So, I mean, I will in fact see a nice question in the worksheet for next week. That's
Haha.
exactly the category where we haven't written down the theorem to deal with this. And you can write down the theorem, but to write down all the theorems that can deal with all the situations is completely counterproductive. So, there one has to sort of argue intuitively, saying, okay, well, this is what happens, therefore that must happen. Right? But you must, of course, be careful that you're not just being flippant, just saying, oh, well, it does this. You have to kind of be able to explain why you believe this is what's going to happen. But
Yes,
there's
I
no
mean,
theorem you can quote for this particular question I'm thinking of.
and saying that you have an intuitive argument is
Mm.
not to say that you don't have an argument. You still have reason for why it is, and
Yeah.
even just explaining that reason is already a good step, right? But
Mm.
later on, we will see how we can formalize exactly
Yeah.
to make sure that we're checking rigorously that nothing's gone wrong. Because some of the most
Mm.
exciting times mathematically for me is when your intuition leads you astray, that you have good reason to believe that one thing is going to happen. But when you
Yeah.
actually try and check very meticulously that it is happening, you see something's going wrong. And then your intuition develops further.
Absolutely.
So, I mean, we've got the limit laws, which they'll be studying. So that is a good tool for making a formal argument,
Yes.
right? Even if we don't prove all the limit laws in detail. But there will occasionally be cases, something like, especially with limits going to infinity, right? That we don't deal with the theory required in order to prove that in full formal detail.
Yeah.
But those arguments are simple enough that, yes, you can make an argument quite well intuitively as to why it happens. But you do touch on the formal definition with the for every m there is a delta, so that you go beyond that m. I mean,
Yeah.
that is the way you would prove it, and you can
Yeah.
build theorems on it to make your life easier to prove more things.
Yeah.
But we're not going to go down that road fully.
No. I think the kind of rule of thumb for limits going to infinity is if basically if 1/f goes to 0 and is positive, then f goes to infinity. That's
Mhm.
the intuition, and it's actually you can prove it, and the proof is actually extremely simple.
Yes.
But I don't want to discuss the proof right now because you
Yeah.
can kind of see that this is going to happen simply by drawing a picture and by doing a couple of sort of computations. You see that okay, well, this is how it should be.
And I would say at this stage, it's really important for our students to
Mm,
start developing that intuition about what's going on,
mm,
right? There were similar questions also with the range. It's like you have to think about what's happening. What are you putting into that part of the function? What is it giving out? How is it going into the next part? What is that putting out?
yeah.
And yes, it can be formalized, but first you need to build an idea of what's going on. And a lot of the maths we do, it's not just that you develop a mechanistic process and you put it through and you get the answer out.
Mm,
It's you build an intuition, you have an understanding what's going on, and then you have formal machinery to check that what you think is happening is indeed exactly the case.
yes.
Okay, so then next week we're really going to dig a little bit further into the limit with a few more properties, and I think we'll also start touching on continuity in lectures.
Yeah, we've got basically I'm making one more video for limits, and in that video we'll start talking about continuity, and then we're going to go smack bam into continuity and continuous functions. I think that more or less covers next week.
Cool. So yeah, and another good worksheet filled with thought-provoking questions and some good lectures. And we only have 3 lectures next week because of the nice long Easter break. So well, we are actually recording this right before the Easter break, but most likely our students will be listening to this during or after the Easter break.
Yeah. Yeah, no, we keep telling our students to work hard, and that's true, but you also need to rest, right?
Yes.
Don't burn out.
Absolutely. It's unproductive to think that you can work hard all the time. Then you start working less effectively,
Yeah,
right? You actually do need to take some days, and I say this for ourselves as well. You have to stop, take some time off, don't look at the maths, right? And come back to it fresh. And actually that is time better spent
yeah,
than trying to work every day, all day through it.
yeah,
You have to give your mind that chance to take a breather.
Yeah, sometimes if you think very hard about a topic and you think about it until you start going around in circles, if you stop thinking about it and a few days later, suddenly it all makes perfect sense. I think it's quite common to work on a problem where you can't solve the problem, and then the next day, suddenly you find the solution.
yeah,
Yes. I mean, the number of times this has happened. For me, one of my favorite stories was a course in honors topology. And I had found a problem in the notes of my lecturer and said, wait, that this can't be the case. It's not true. And we had a discussion and it was unresolved. And we both went and slept on it. Now, I don't know if he wasn't sleeping very well or what was happening, but 3 o'clock in the morning, he sent me an SMS and it read, no, it works. It's actually very easy to fix. And I was half through the sleep looking at this SMS. I'm like, oh, I'll think about it tomorrow. I'm going back to bed. And I slept. And when I woke up, my first thought was, yes, it is very easy. This is why.
yeah. There's There's a story of Poincaré, who was a very famous mathematician of the late 19th, early 20th century, who was thinking for a long time about a difficult problem and then stopped thinking about this and went on a geological expedition and was always also interested in geology. And the story is that as he put his foot on the train, the solution came to him immediately. It's just like, oh,
Beautiful. So we hope our students are either enjoying or have enjoyed a nice breather, and that they all come back recharged and ready to tackle our next topic.
yeah, absolutely.
Okay, so I think that's it then for this calculus chat, and we'll be seeing you online. Goodbye.
Goodbye.
Bye.